staying so close to linear here. Okay, so the title should be some proof system for MaxSAT. And actually, more close to what I'm going to talk will be some variation of MaxSAT-Resolution. So in some sense, it's some talk that is like a team. I want to, that will be kind of easy, like to use. And then there will be some variation that might not be so recognizable from the team, but okay, so what is the thing that I want to talk about is like weighted resolution and MaxSAT. So it would be the proof system for MaxSAT. And then some variation that would be depth Sherali-Adams, whatever that means for the moment. And then MaxSAT on polynomials and how to use this idea of weighted proof system to define a weighted polynomial calculus for MaxSAT. So please interrupt me in any moment with questions. I can start. Okay, so weighted MaxSAT, this is mostly to fix some notation. So we have a multi-set of clauses with weights. And the weights intuitively mean how unhappy we are if we have an assignment that falsifies that clause. And the measure of our unhappiness will be the sum of all the possible weights of the clauses that we falsify. We want to minimize this cost, this unhappiness. And for the purpose of this talk, we are interested in proof system to certify that the minimum cost of this unhappiness is at least some value down. And by the way, so I will be talking about MaxSAT. So implicitly will always the MaxSAT context. But if you want, you can think, okay, the weights of the initial multiset, they are not part of the input, they are part of the proof. So you could choose it, and that will be sum. So everything will have this double interpretation as SAT or MaxSAT, depending on if the weights of the input are, you think of them as fixed or as a parameter that you can choose in it. Okay, so this will be the thing. So yeah, it's a generic template of how to construct proof systems that will work for MaxSAT. So this will be like some framework that is kind of in the space context, like memory configuration kind of thing. So at the beginning, at time 0, there will be this grading that will be a multi-set of clauses, the input. Again, you can think that's the weight as given or that could be chosen. And now at time 1, there will be some operation, substituting some of the clauses with some other clause, and that will depend on the system. And then we keep doing this, and eventually at time L, we arrive to a set of clauses, a multi-set of clauses that contains the false clause with some weight, and then other clauses. And now for this to be something good to certify that the weight is at least some value, we need that for every time step to the next, for every assignment, we preserve the cost. So the cost dimension. So we need to design rules such that they have this property. And now if we have this property and the other clauses that are in the last time step together with the false, all of those other clauses are satisfiable, then the minimum cost will be W. The minimum cost of what? Of the initial multi-set of clauses, the one that we actually cared about, the input. But if we only care about proving lower bounds for this quantity, it's enough, for instance, to have all the weights, the other clauses to be non-negative. That will also certify that the minimum cost is at least some value. So questions about this template? It's mostly a picture, so I know you might be confused. Okay, so what are the type of variations that we can do? There are a lot of them. So first of all, what are the objects that we want to put in these multi-sets? They could be clauses, bounded formulas, polynomials, something else. What are the weights? The weights could be integer numbers, natural numbers, or just 1, or plus or minus 1. The 1 and plus or minus 1 will correspond to unary version of the systems. Or we could also change the condition on FL, which I mean changing this part to other things, and that will correspond to different systems. Or we can also think of this for MaxSAT instead of think of this framework for MaxSAT. So, okay. So just to be a bit more concrete, what are some reasonable rules that we can use? For instance, the rules of weighted resolution. And now this Z depends on where I'm thinking the weights of these clauses to live. So the rules will be like the symmetric cut from one time step to the next. You can substitute two premises with the conclusion, or substitute one clauses with the weakening with the variable and the opposite value of that variable in the next time step.
So are these destructive rules, or?
Yes, they are substitution rules. And right, and then if we are over Z, there is also the other rule that from nothing you can put there whatever clause you want, but you have to somehow commit to prove it at some point. So there will be the clause with weight W and the tail clause with weight minus W. And of course, there will be other rules that are less interesting, like how they behave on the weights. Like if you have a clause with weight W and a clause with weight V, then it's two different weighting clauses, you can put together the weights. So these rules are less interesting. Okay, so something that I have to mention. Over Z, these rules are redundant. So for instance, either one of the two, either the split or the symmetric cut is enough. But over the natural numbers, of course, over the natural numbers, this rule is not there. But the other two, now they are needed. So that's why I put all the three rules, because implicitly here, there is also a definition of weighted resolution, but only the weights are just positive numbers. Only the rule you cannot apply because there are no negative. Okay, so this system is a different way of describing circular resolution and also Sherali-Adams. Now, Sherali-Adams can talk naturally about polynomials. So what I mean when I say this is equivalent to Sherali-Adams, only on some natural encoding of clauses into polynomial. So a clause will be a product of variables. So this equivalence with Sherali-Adams is only on this type of propositional polynomials encoding to position. So this will be Sherali-Adams, and now my claim is one of the variation will be, okay, this is a generic template that one can use for Sherali-Adams, Nullstellensatz, and sum of squares. The only difference, so the rules now they are the same. What changes is the condition that we have at the end to ensure the soundness of the system, which is, for the case of Sherali-Adams, will be clauses with positive weights. For the case of Nullstellensatz will be weakening of initial clauses. And for the case of sum of squares, it will be something that looks a bit artificial with this language. So the idea, so how that these are related to the algebraic world is just basically if we have a clause that I don't know is a weighted clause X or not Y with weight 3, these will correspond in the algebraic world to not X or Y with minus 3 in front as a coefficient. So it's a direct translation, and a multi-set will correspond to the sum of these monomials that you have corresponding to the clauses. I don't want to focus that much on this variation, but there are questions. Okay, so this is somehow one picture, and then put this connection with other stuff. Okay, so there is sum of squares that is stronger than Z-weighted resolution, which would be for simple resolution. There are two possible restrictions. So this one is natural weights, and the other is just plus and minus 1 weights. And of course, a common system that is weaker than both will be just the weights that are just ones. So the weaker one will be corresponding to reversible resolution, but that was in the context of SAT. So you have the freedom of putting the same clause with multiplicity. Here, if we are thinking in the context of MaxSAT, the initial weights of the clauses are fixed. The multiplicity of the clauses is fixed. And yeah, and so weights plus and minus 1 will correspond to unary Sherali-Adams, which also can be used in the context of MaxSAT. Just think of the polynomials that you want to multiply your axiom just to be minus 1 or minus the weights that you want for that.
Yes. These are for small proofs in these systems.
Sorry? Yeah, so, yes, thanks. So the translation is so direct that the weight of these clauses will be the degree. So then the notion of so in these systems you have a notion of degree that would be the width of the width of the closest element.
So in the diagram, you mean small degree?
In the diagram where there is this squiggly equality with PPID and stuff, I mean small narrow version of the system. That's why there is the squiggly. I mean, yes. But the connection to this system, of course, as we saw earlier in this week, is important because, for instance, the separation between the two systems was based.
And how essential is the configuration model with substitution?
That's also a very good question. So this looks like a dynamic system, but it's really not a dynamic system. So you can rearrange the configuration freely, essentially. So this will correspond as like, suppose that you are given like a Nullstellensatz equality, some algebraic expression equal to 1. Now you want to check that it's correct. So the configuration will correspond to partial sums towards verifying this thing. And also, of course, this could be used as to give a notion of space for this system, how costly with respect to space is to verify the correctness of the sum of squares proof. So, right, so the next variation will be depth Sherali-Adams. So I will not spend that much time, but so the idea is like, okay, we can use the generic template. Now we don't have clauses, but we can put together there as object depth formulas, right? So you can define bounded at Frege, there will be a symmetric cut. Now there are not clauses, there will be formulas and a symmetric split and some other extra rules to make it complete. And so there is a way to make that work for MaxSAT, for bounded depth formulas. And we can think as this, since it's very similar to this language, as a depth version of Sherali-Adams. Right, so this is not a proof system that come out from nothing. It's equivalent to circular depth Frege. And how strong is that? So for instance, the unary version of this system, so the weights will be only 1 and -1, is strictly stronger than depth Frege for depth up to log n over log n. So that means it's either related to Zeitin or the pigeonhole principle, because for that depth there are not many lower bounds. That's the pigeonhole principle. Yeah, so basically because Sherali-Adams is able, unary Sherali-Adams is able to prove the pigeonhole principle, but that's harder for depth Frege up to that depth. And also, at least the unary versions, they are polynomially bounded. For instance, the parity is hard to refute in these systems. And that's because all these systems, they are below depth. So the depth version of unary Sherali-Adams is below depth Frege plus the pigeonhole principle. And since parity is hard, even in bounded at Frege, even given the pigeonhole principle, then for free there is this. Okay, so the other variation that I want to spend the rest of the time will be MaxSAT on polynomials and weighted polynomial calculus. So the idea is very similar. Now, instead of clauses, we want to have polynomials. So what the analog of MaxSAT on polynomials would be, okay, we have a multiset of weighted polynomials. Again, we want to satisfy, that means evaluate to 0 as much polynomials as possible. And these weights are measuring how we are unhappy if the polynomial, when we evaluate it, is not zero. And the idea is that, okay, this allows a bit more flexibility at the level of encoding. So if, for instance, MaxSAT can be encoded directly as degree 1 polynomials in this language. And yeah, so we want to work in this setting, and we want a system that will take that are arbitrary weighted polynomials, some finite field, and produce a sequence of configurations with rules that are preserving the cost. And similarly to weighted resolution. This is a way that we propose to do that. So it's using the same template. So from one time step to the next, and now there is these substitution rules. And right, so I will go back on why they are sound, they are cost preserving. So for the moment, I don't want to make general comments on the rules, which are, again, they are redundant for the weights that are in Z. And also there are structural rules about the weight behaves like before, like weight resolution. But also there are rules to identify polynomials, like we want to identify these polynomials, this polynomial and the polynomial 0. Of course, as polynomials, they are different. But since we are only interested as how these things behave when we evaluate them, if we are over F2, this thing and 0 are the same. They behave the same. So for instance, when we multiply like this product of two polynomials, when there is this xz times z plus 1, this is 0. So this is the same. We treat it the same as this polynomial, yz plus 1. Right, so for simplicity, I wrote the rules for F2. There are rules also for every arbitrary finite field that makes sense and give rise to a sound and complete system.
So are you going to say why? I mean, the middle rule looks a little odd. So
yes, I will say it in 2 slides. I will
okay.
going to say why. Yeah, the middle rule looks odd, but they are equivalent. So
Equivalent to what?
to the first one. So they're redundant. If you have the third rule and only the first one, you can simulate the second and vice versa. So, right. So this is basically, this is sanity check that what we are doing makes sense. So, okay. So we have a multi-set of weighted polynomials. Now they might be then the propositional encoding of a CNF formula. In this case, the completeness is for free because MaxSAT-Resolution is complete. But it might be arbitrary polynomials, so it's not obvious that you can certify the cost for an arbitrary set of weighted polynomials. And so, right, so there are 2 results. The soundness, so if we have a derivation in this system, then we derive one with some weight, then the minimum cost is at least W. And vice versa. If the minimum cost is exactly W, then there is a derivation in this system where we only use positive weights. Actually, the first rule is even in a weaker form and is still complete. Right, so there is a derivation in the system of the polynomial 1 with weights W. Right, so now there is this, table where the weights, they might be natural number, integers, plus or minus 1, just 1, and now the coefficients of the polynomial. All of this could be phrased in a purely algebraic language, but now if we want to do that, then it might be more confusing because at the same time we have always 2 sums, the sum in Z and the sum of F2. So somehow this language is somehow hiding the algebra of how these things behave on the N and Z with algebra back from the finite fields. Okay, so unless you ask, I will not plan to write down the rules for the FQ system, but of course I can write it down. Right, so now, okay, so now to your question. why this thing is sound? So the first rule, it should be okay. No, the first rule is like, okay, you have a polynomial. If it is 0, sure, these 2 other things are 0, the cost is 0 before. Okay, so now if this polynomial evaluates to 1, now under a total assignment, now either Q is 1 or Q is 0. So if Q is 1, then this thing is 1, and this thing is 0 because we are over F2. So, and vice versa. If Q evaluates to 1, to 0, then this part will not be satisfied, and this will be satisfied. So nothing. Okay, so for the sum, the tricky thing is when both of them evaluate to 1. So if both of them evaluate to 1, then the sum is 0, so this is 0. And now the product is 1, so this is. And if only one is 1 and the other is 0, this part is 0, and this part is 1, so the cost will be the same. If both are 0, the consequences are in the ideal. So. Okay. Better now? So okay, so the rules are redundant, and if we are over Z, and yeah, there's not much more to say about those. Okay, so the completeness. So what is the procedure that we devise? Is based on some similar idea for MaxSAT-Resolution, but in MaxSAT-Resolution it was much simpler. Here is a bit more tricky. The idea is to use some sort of saturation. And the important property that we want, so I will describe informally intuitively what for a set of polynomial to be saturated means, which will be this thing. But the useful thing about saturated set is that if we have a set of polynomial that is saturated with respect to a variable, then setting for every assignment that we have, setting that variable to 0 or to 1 satisfies all the polynomials. It's not just that the set of polynomials is satisfiable, but if you are given an assignment on the rest of the variables, you can satisfy all the polynomial containing x, setting that value. So for instance, set of polynomials x plus y with 1, and x plus z with weight 1. This is not saturated because if you give me an assignment that we say y equals 0 and z equals 1, and there is no way to set x either to 0 or to 1 to satisfy both polynomials. Right? So this we are given this set of two polynomials. This is not saturated. So, oops. Sorry. Okay, so this is the property that we want, and now a set of polynomials will be saturated with respect to a variable. Essentially, if we have done all the split and sums that make sense. So we are producing all the possible splits of polynomials up to we don't get any new non-trivial polynomials. Polynomial will be trivial if it is equivalent to 0. So informally, this is the notion of saturation and how it's used. So we start with our initial set of polynomial, we saturate it. There will be some polynomial containing the first variable and some polynomial that don't contain the first variable. And then we keep saturating. So this set of polynomial without the first variable, we saturate it. It will be a part containing x2. We saturate it with respect to the second variable, x. This fashion, one variable at a time. And eventually we arrive to a set that has this kind of onion shape, and we derive the false with some weight. And now the property of the saturation makes, okay, we can extend these to satisfy all the polynomials with xn, then x minus 1, and so on. So eventually, everything that is here, apart from the false, because of the saturation, will be satisfied. So this is a quick intuition about how this theorem is proved. And actually, this proof will use only a weaker version of the split rule. That's not so relevant. Okay, so basically, why this system will be kind of interesting because you can use it. Polynomial calculus over F2 and Sherali-Adams, they are like water and oil, they don't mix. No, one is able to do the pigeonhole principle, one is able to do citing, parity reasoning, they are completely different words. So obviously they are incomparable, but this system somehow can mix the two things. So now in this system, both the pigeonhole principle and citing are easy. So it's like, could be seen as a way to extend Sherali-Adams to allow parity reasoning. And of course, we can, with that trick of seeing sum of squares in this context, we can also do it on sum of squares. It would be just a different sumless condition at the end. And now you could have sum of squares that is with parity reasoning. And right, so one question is, okay, how these two systems compares? So for sure, sum of squares is not able to do parity reasoning, so it's not possible that sum of squares simulates this system. And it's an open question to see if the other way around holds. Likely not. Yeah, so I wanted to spend the last 3-4 minutes to say some open problems and motivate them. So the first one was about this empty version of Sherali-Adams. So there is this Sherali-Adams using formulas of some depth instead of clauses. So now, is it perhaps possible that you have a unary version of the system? And now, if you go to higher depths, will this simulate Sherali-Adams? So can you trade coefficient size for depth of the formulas? Of course, for some depth that is not making the system super strong, like Frege's. Please correct me if I'm wrong. So I think this is open, and I find it interesting as a possible question about the system. Okay, so what about this polynomial calculus that I defined? So, okay, so there are a lot of questions about it. The first one is, okay, we gave a procedure for the completeness, but it's not in a reasonable degree. So is the system degree automatable? So can we find proofs in this system of degree d in time n to the d? That is not obvious, but both of these systems, they are degree automated. Sherali-Adams and polynomial calculus over F2, they are Robner basis and linear programming. They both are degree automatable, so perhaps some merge of the two paradigms will automate this thing. It's not clear. Yes. The other question is, okay, lower bounds for these systems and separation from some squares. And yeah, a natural candidate would be the bit pigeonhole principle, perhaps, because it's hard for Sherali-Adams and it's reasonably hard for polynomial calculus, but it's easy for some squares. And now a question that is not directly related to this talk, but I like it, well, it's just directly related, indirectly related, which is it possible to simulate resolution in unary sum of squares? Probably not, but I would like to see a proof of that. So thank you very much. And
questions?
Do you have size degree trade-offs for?
that's also a very good question. Yes. Yes. Yeah, it's also so. I mean, that's also a natural question because we have size degree trade-off in both the weaker systems. Yeah.
Any candidate for lower bounds for PCF to Sherali-Adams random formulas?
Yeah, sure. Random formula is always a candidate. But I was thinking of the bit pigeonhole principle. That would be much probable. Or perhaps random formulas.
For the characterizations of like Sherali-Adams, you have these like resolution systems. Is it possible to get a resolution system for polynomial calculus? Like something where every line is a clause. Does that make sense?
Polynomial calculus over the reals or what?
Like anything really, yeah.
I mean, in this system that I described, the lines are polynomials.
Hmm.
But it's trying to achieve something more, like to be sound for MaxSAT.
I see. Okay.
If you just want a line-based thing like that, you could do the same trick as resolution. You put weights, and then you consume things, but it's like since from the beginning you put knows all the polynomial with the multiplicity that you will need in your proof.
Oh, okay.
I mean, the difficult thing here is to have the insight we want was to have something sound for MaxSAT, because normally the rules for polynomial calculus, they're not sound MaxSAT. You could have two polynomials that are one, but now the sum is zeros.
Gotcha.
Should have stressed.
So I think it's time to go. Let's thank the speakers again. And at 8 after dinner, there's music night.
Music down.